Hello everybody and welcome to the latest edition of the Physics Corner. I am your host, Dr. Christopher Sorolla, and this is a video series in which we set up and solve interesting introductory physics problems for students. So today we're working on an elastic collision problem with a bit of a twist. In this particular case, one of the carts is larger than the other. Specifically, we have a cart we'll call cart A, has twice the mass of this cart over here called cart B. Cart B is originally stationary. Cart A will have an initial velocity of 1 meter per second. After they collide, of course, the two carts will be moving apart from each other. How is the question? So this particular question is a little bit more intense, if you will, or involved than some of the other questions we've asked in some of these videos. So, fair warning, first off, there's going to be a decent amount of algebra to solve this. And second, it might help if you view the video on elastic collisions part 1, in which the two carts had identical masses. So you can see a bit of a preview and a simpler version of the algebra. But in any case, let's get started. So, what are knowns and unknown quantities? They're not going to be any different than they were in the previous problem, except with a little bit of a difference. So, we know today that the original velocity of cart A is 1 meter per second, and the original velocity of cart B is 0. We define that as stationary. Okay. We also know the relationship between two masses. It says specifically the mass of cart A is twice the mass of cart B. That's going to come in handy to know specifically. So, what our unknowns will be the velocities of both carts after the collision. We'll call that the velocity of cart A after, or final velocity of cart A, and the final velocity of cart B, we'll say VBF for that. So what are the equations or formula that we need to have in our pockets in order to do these? This is an elastic collision. During the collision, momentum is conserved. So momentum going into the problem is the same as the total momentum coming out of the problem. That is for the system of objects, if you recall. And the momentum of an individual object is simply mv. Also, because this is an elastic collision, we're going to also make the assumption that the kinetic energy of the system is conserved. And we can write that idea like this. And again, as a reminder, the kinetic energy formula for an individual kinetic energy is that formula. Okay, so these formulas are doing different things, mind you. These two statements here are conservation statements that involve systems of objects. Our system being carts A and cart B. These two formula are formulas for individual ideas. So what is the individual momentum of an object? What's the individual kinetic energy of an object? We need those two. Okay, let's go ahead and start applying. So usually it's simplest to start with the momentum formula, so let's do that. So total momentum coming into the problem for the system is the total momentum coming out for the system. And since we've already covered this in a previous video, I'm going to go a little bit faster in some of the setup. The momentum coming in is only due to cart A because cart B is stationary. Individual momentum is mass times velocity, so mass of cart A multiplied by the original velocity of cart A, like that. Now, by the way, we know that that number will be 1 later on, but let's hold on to the symbol for the moment. We'll put in the number 1 when we have to later on. After the collision, we don't know which cart has what kind of velocity, so we have to treat those both as unknowns. So mass of cart A, final velocity of cart A, like that, and mass of cart B, final velocity of cart B, like that. So those are our two unknowns. We have one equation, two unknowns. As we all know, we need two equations with the same two unknowns in order to solve that system. So let's get our second equation, the kinetic energy conservation. So kinetic energy in equals kinetic energy out, again for the system, or for both objects together. In this particular case, 1/2 ma VAO squared for the kinetic energy of the incoming cart A. Remember, again, cart B has no incoming speed, therefore no incoming kinetic energy. After the collision, it's 1/2 ma VAF squared and a 1/2 mb VBF squared, like that. Again, also as a reminder or as a discussion why we're doing this, notice we have lots of subscripts, right? Well, we've got two different kinds of things happening that we need to distinguish for the subscripts. One is there's two different carts. There's cart A and cart B, but also there are two different times for the velocities we're interested in. Immediately before the collision, which we're putting a naught on, and immediately after the collision, which we're putting an F on. So original and final, if you will, or before and after. I didn't want to use A and B for the subscripts because we've got A and B for the cart names. So original and final for my subscripts there. That's my logic for that. Okay, so let's see if we can simplify these equations and put them to use, right? Well, let's take a look at this equation here first. So I'll rewrite that one down over here, okay? So the mass of cart A, we say, is twice the mass of cart B. So let's actually just write it that way. So 2 times the mass of cart B times velocity A original. Again, MA is 2MB, so 2MB VAF here. And then we don't need to change this, it's already in MB terms. And it looks like that. Okay. What's the advantage of rewriting it this way? Because now we can see that MB is common to all the terms and we can get rid of it like this. So we're left with an equation that has this appearance, like that. Okay. One more thing, I'm going to look a little bit ahead, okay, in having done the problem, as you might expect beforehand. I'm going to look a little bit ahead and make one slight adjustment to this equation, which will come in handy as we go along a little bit later. I'm going to go ahead and divide everybody by 2. And if I do that, then the final version of this equation will look like this. And it looks at first glance like this might cause us some issues because I'm introducing a fraction where I don't have any. But it turns out when we do the algebra a little bit later on, that will come in handy to have made this little transition. So looking at that, so that's one of our equations simplified. Notice we've gotten rid of all the masses. The reason we were able to do this is because we knew there was a relationship between the two masses here. All right, so, all right, that's our first equation. Let's take a look at our second equation. Let's take a look at the energy equation again. I've recopied it here for our benefit and just noted the relationship between the masses of A and B carts, okay? So let's substitute this in over here quick. I'm gonna leave the 1/2s alone for a moment. So I have a 1/2, a 2MB instead of MA, right? VA naught squared like that. Oops, that should be an equal sign. A 1/2, again, 2MB here. VAF squared, and I don't have to change MB, it's already there in this last term. 1/2 MB VBF squared like that. Okay, let's see if I can simplify. 1/2 is common to all terms. That's why I left it alone. And then MB is common to all terms. So I can also take care of that. And this equation simplifies to 2 VA naught squared. I have a 2 VAF squared. And there's no 2 here, just VBF squared there. So that's the second of my simplified equations. All right. So let's bring back the other equation for comparison's sake. All right, and that was VA naught equals VAF plus a 1/2 VBF like that. So those are our two simplified equations. Again, we can do this simplification because we know of a relationship between the two masses. If the masses were both unknowns, we'd have a really big algebra fight on our hands. That isn't to say it couldn't be done. It can, it'd just be really messy. It's really helpful to know some information going into this situation before we get started. Okay, so what I want to do is solve for one of these and then substitute up here. I'm going to choose this. I've looked ahead again a little bit. Let me choose this one. So let's solve for VAF. So taking this equation, solving here, is VA naught minus a 1/2 VBF, like that. And now let's square it. So VAF squared equals, now if you're really good or comfortable with your algebra, you can probably skip this part of it. I, for these purposes here, prefer to show all of it off so we can see exactly what's happening and why. Okay, so let's do it that way. Okay, so VA naught multiplied by VA naught gives us VA naught squared, no surprise. A negative 1/2 VBF, VA naught. This shows up here with this term and shows up here with this term. So there's two of them. As you might remember how that works a lot. Negative 1/2 and another negative 1/2 gives me -1. -1 VBF VA naught. And then at the end, a negative 1/2 multiplied by negative 1/2 is a positive 1/4 VBF squared that way. Okay. One more little trick to do. If you look in this equation here, it's not VAF squared, it's 2 VAF squared. So let's take this and multiply by 2. So take this whole thing right here, multiply by 2, and that becomes 2 VAF squared. This also going to multiply by 2, right? Equals 2 VA naught squared minus a 2 VBF VA naught, and plus a 1/2, because 2 times a quarter is 1/2, right? VBF squared like that. Okay. So I've gone ahead and done that little transformation. That way, this will fit in here. So that's the next substitution. All right? So 2 VA naught squared equals all this stuff. So 2 VAF squared is this. Let's write it down. 2 VA naught squared, a 2 VBF VA naught, and a 1/2 VBF squared there. And then don't forget, that was just this term here. You have this piece left over as well, so add this at the end. VBF squared there. Okay, so here's the payoff. This is why we did some of the tricks that we did looking forward, is to get this to happen. 2 VA naught squared, 2 VA naught squared is on the same side. We can get rid of it consequently. That's going to make a big difference, right? And it helps a lot. Okay, what else we got? Well, we have this term and this term to play with now. So let's take a look. Let's add these together. They're both squared terms. 1/2 plus 1. 1 is the same as 2/2, right? So 2/2 plus 1/2 would be a 3/2. So 3/2 VBF squared there. I don't have to add anything, you just write this. Minus 2 VBF VA naught. And now that other side is 0. So we have this. At this stage, it's a matter of cleaning it up to make it look the way you might like it to look, or to make it clear. I'm going to multiply both sides by 2 just to make it look a little more pretty. You don't have to necessarily, but I'll do that. So let's multiply everybody by 2. That way I just have a 3 VBF squared. 2 times 2 here is 4. 4 VBF VA naught. 2 times 0 is still 0. Get that. Now I can separate these two out and solve. There's a VBF common to both of these terms. Let's pull that aside. This term, I'm left with another 3 VBF. We have a 4 VA naught, subtracted mind you, equals 0. And here's my solution, algebraically, that I've been looking for. This is in order to get me the final speed of cart B. Remember, going through all these subscripts, we're using the subscripts as shorthand for ideas, right? To stand for something. VBF, remind, what does it stand for? It stands for the final velocity of cart B. So that's what I'm looking for here, right? That was my purpose all along, is to find the final velocities of the two carts. Here's one of them. Okay. So this possible solution would be either two solutions, VBF equals 0, right, to make this work. That's really basically the statement that cart B was standing still to start with. Or this statement, 3 VBF minus 4 VA naught equals 0 like that. Solve for VBF. VBF equals what? A 4/3 VA naught. And if you plug in the 1 meter per second, 4/3 of a meter per second, like that. So now, by the way, carefully look at your signs. That is a positive number. So does this make sense? At least in first glance it does. So when cart A comes barreling in, it hits cart B and it's going to knock it forward. So having a positive sign in there makes some sense. Also, cart A is more massive than cart B. It has more inertia, which means it's easier to change the velocity of cart B. So it changes a lot. It changed from 0 to 4/3, which of course is bigger than 1. So cart B gained a lot of velocity. Now, there's a couple ways to go about solving for the velocity of cart A after the collision. I'll show you the algebra here because that's what we're doing. But just to note something about it all, there's a trick I'll show you later on that we could have done to shorten it up. So let's write down what we had there. VBF was equal to 4/3 VA naught, like that. Or if you prefer, 4/3 meter per second. That's why I chose 1 as my initial velocity, right, to make everything simple. And go back, one of the statements we made originally, if you go back far enough, was VAF was equal to VA naught minus 1/2 VBF. Okay, let's plug this in here. So VAF equals a VA naught minus a 1/2 multiplied by 4/3. Let's keep VA naught in here for the moment. Again, I can always put the number back in there when I want. And let's see, so this becomes what? This is 4/6, so minus 4/6 VA naught is this term here. 1 times 4, 2 times 3, right? For VA naught, probably simplest to write it in terms of sixths, so it's one of them, or 6/6 VA naught, like that. It's a simple transformation, okay? Now, because they're both sharing the same denominator, I can subtract. 6 minus 4 is 2, so I get a 2 divided by 6 is 6/6 VA naught, or a 1/3 VA naught, or if you prefer, 1/3, and again positive, meters per second. So let's think about this. The speed of cart A dropped, as you might expect, right? It was going forward. It hit another cart. It had to give up some of its energy to that second cart, to cart B. Therefore, it's not going as fast. But by the same token, it's still going forward. Why is it still going forward? Well, it had a larger mass, right? It had more inertia, if you will. It had the larger inertia. That's what mass is, right? Mass is a measure of inertia, the tendency to resist change of motion. So its motion changed from 1 meter per second to 1/3 of a meter per second, which is a drop. But as a comparison, if you go back and watch that video on the case where the masses are identical, it didn't drop as much. When the masses are identical, all of the velocity was gone from cart A. It completely stopped. Here it doesn't completely stop. It keeps going forward a little bit. Okay. One more thing. So let me write this out in front of us so we can see them together. You can see kind of an interesting trick we have here, and I'll circle this as well. There we go. Look at those. Take a look at this. 4/3 minus 1/3 is equal to 3/3, which is 1. But 1 was the original velocity of cart A, wasn't it? Which is to say, this is a kind of an interesting math thing that pops out, and it's a shortcut. And if you want to talk about it that way, if you have an elastic collision, purely elastic collision, that the difference in velocities of the two objects after the collision will be the same as the difference of the velocities before the collision. Okay, remember cart B was stationary, so to start with. So cart A compared to cart B to start with, the difference was 1 meter per second. Check it out. After the collision, the difference is still 1 meter per second. Kind of an interesting thought there. Okay, that's a bit of a trivia bit, but that's what that is. Just kind of a side note. All right, so what was the point of this here? This is a little bit more of a deeper exploration into elastic collisions. A couple of reasons for doing it. One is to show you that elastic collisions are more complicated, more structured, take more time, more effort to solve than inelastic collisions. It sounds like it should be the opposite way around, right? Because you have more information for an elastic collision, but you also have more to solve for. You have more conditions to play with, which again, sounds like that gives you more to help you, but actually is a little bit the other way around. You have more to keep track of. And therefore we have two equations, two unknowns to solve for, rather than say the one equation and one unknown with the inelastic collision. So elastic collisions are a little more difficult. Also, this does show off what we expect to happen. Because cart A is more massive than cart B, it tends to kind of barrel through, if you will. It tends to keep on going. It has more inertia, right? Cart B, because it's lighter, flies off with a faster speed than you might expect, because it's easier to change its motion, it has less inertia. And that's what you're finding here. Okay. In a different video, we'll take on the case where cart A is smaller than cart B, but that's a different case. I'm pretty sure that this has been enough for one video. All right, everybody. Technical support comes from Sidney Gautraw and Sophia Turner. Funding is from the University of Mississippi and University of Southern Mississippi. These videos are filmed in Hattiesburg, Mississippi. I'm your host, Dr. Christopher Sorolla, thanking you, as always, for your attention and clear skies.